Hello, everybody. Welcome to lecture 18. In today's lecture, we will learn logarithmic functions and properties of logarithmic functions. So what is a logarithm function? Well, in our last lecture, we learned exponential functions and we learned inverse functions. If we have a function f of x, we said the inverse of this function is denoted by f inverse, which is written in this form of x. So this, we call it an inverse function of f of x. And to check if two functions are inverse or not, we had the property, which is the composition of the functions. Let's say if f and g are inverse of each other, then the composition of these two functions is x, or the other way, composition of g and f, or g of f of x, is again x. So this is how we check whether two functions are inverse of each other or not. Now, since we are familiar with exponential functions are functions which are given in the form of b to the power of x, where b is a constant between 0 or 1 and 1 or greater than 1, and x is the variable, right? So this type of functions, we call them exponential functions. Now, the inverse function of such a function is called the logarithmic function. Okay, so going to the formal definition of these logarithmic functions, let's say we have x and b, where both of them are positive real numbers, and b is different from 1, then this function given, or this equation of two variables, y equals to log x the base b, is called the logarithmic function of base b. So this is called, the b is called base, and the x is called the argument, okay? And then the y is the logarithm, okay? So this is what we call the logarithmic functions. Now, if we have y equals to log x the base b, then this is equivalent with writing b to the y equals to x. Now here, this is exponential function. Okay, this format is exponential form. As you can see, this one, y is a variable and b is a constant, so we have an exponential form, and this is a logarithmic form. So whenever we have a logarithmic form, we can always rewrite it into exponential form, or if we have exponential form, we can rewrite it into logarithmic form. For example, we have y equals to log 8 to the base 2. We have y equals to log 8 to the base 2. Now, we need to follow this relationship to write this one in exponential form. This will be the base of the exponential form, and this will be the exponent. So 2 to the power of y. You see, this is the exponent, and the 2, it is based to the logarithmic form, and it will be based to the exponential form. So we will have to the power of y equals to whatever we have this number, which is 8. Okay, this is what we have. Then to the power of y equals to, now we write this one in exponent form, and 8 means 2 to the power of 3, right? We can write this one in exponent form. Therefore, we have the same base, 2, 2, and we have y equal y and 3. Therefore, if these two numbers are equal, then that means y should be 3. Okay, y should be 3. We will see this one in later in a moment, because we have properties of logarithms. And similarly, if we have this, if we have y equals to log 25 base 5, then we can write it as 5 to the y equals 25, but 25 is 5 squared. Therefore, y and 2, they have to be the same, right? Y and 2, y should be equals to, in order this in order this to be equal. Okay, so let's say we wanted to write a logarithmic form in exponential form. So if we have an exponential form which is given in this form, a logarithmic form, this is log 64 to the base 8 equals to 2. So this is the base to the logarithmic form, and it will be base to the exponential form. So for exponential form, base is this one, the exponent is this one. Okay, this is the base. Therefore, now here we have base and exponent. So what we do is we bring this one and raise it to this one. So we have 8 to the power of 2, and then we just write this one. So the trick or the thing is just bring this 8 here and put it under 8, or just raise this 2 to 8. Okay, or I should say the other way, 8 raised 2. Yeah, that should be the proper way. So we have 8 to the power of 2 equals to 68, and that's true. This is 64 equals to 64. And we have, let's say we have log. So we will learn this one in a minute. But let's say we have something that doesn't have any base here. I will take the same example. If we have, for example, something like this, then you may ask, well, where is the base for this one? It doesn't have any base. Well, this is something that we call common logarithms, and it's obvious that we don't write the base here. So whenever you see something like this, it means it's base 10. Okay, there is a base 10 here. Okay, so here I can rewrite this one in this form, and then we can rewrite this one in exponential form. So the base here is 10, and then the exponent is negative 4. So 10 to the power of -4, which is this, equals to 1 over 10,000, and that's what we have right here. Okay. So here we have the properties, the equivalence, from logarithmic to exponential, which is basically what we have right here. Okay. If we have this logarithmic form, then this is the same way as this exponential form. Okay, so we use this property to go back and forth, to go from here to this one, or to go from the exponential form to the logarithmic form. And log 1 to the base 4 equals to 0. Well, why is this 0? Well, let's write this one in exponential form. If you write this one in exponential form, then this will be the base and this will be the exponent. So we have 4 to the power of 0 equals to this number, which is 1. And 4 to the power of 0, any number to the power of 0, any number x to the power of 0 is always 1. Therefore, 4 to the power of 0 is equals to 1. And that's what we have right here. And then to write an equation in logarithmic form, so we have these exponential forms, and we are asked, or we wanted to write them in logarithmic forms. Now, let's start with the first one. We have this. So this is the exponent in this case, and this is the base. So the base is always the base whether it's to the logarithmic or to the exponential form. So what we do is we bring this one right here. It will be base here, and we add log here, and we bring this one down. So basically it will be 3 equals to log 125 base 5. Okay, I just put it on the left side, but it doesn't matter. So that's what we have right here. We will learn this one in a proper way because we have properties that will help us rewrite these things. Okay, but what you do is normally the idea, if this is your first time, well, not first time probably, but if you don't remember the logarithmic forms, what you could do, the trick is just put this one down here and then bring this one the base, bring this one as base here, and add a logarithm here, okay? And then you will be more comfortable once we learn the properties. Okay. And of course, we do the same thing with this this one as well. And here we have the equivalence property. And this is very important, and because it helps us to solve or to evaluate logarithmic forms or even exponential forms, of course. Okay. So let's say we have this b(x) and y, all real numbers, with b greater than 0 and b different from 1. Okay, we don't want b to be equals to 1 because that's not going to be an exponential anymore. So if we have b to the power of x equals to b to the power of y, which means basically the same base, then that implies that x and y have to be the same. Otherwise, this cannot be equal. Okay, so this is very important when we evaluate or when we solve exponential equations or when we evaluate exponential expressions. And similarly, because of this relationship, since we can convert a logarithmic form into exponential form, so if we can use this one to solve exponential form, we can use this one as well to solve or to simplify or to evaluate logarithmic form as well. So we have an example here, a simple example, that we are asked to evaluate this expression. Okay, so the first thing, because we haven't learned anything to evaluate this one through logarithmic form, the first thing that I need to do is I need to convert this one to exponential form. So we are trying to find what this value is. So what I'm going to do is I will just put equal here, equals to x, just random variable x. And now I will convert this logarithmic form into exponential form. And this, from what we learn, is we bring this one here, and this will be the exponent, and this will be the base. Okay, so 1/64 equals to 4 to the power of x. And now let's write 64 in terms of exponent, okay, in exponential form. And 64 is 4 to the power of 3, right? Because we have 4 times 4 times 4, that gives us 64. Therefore, 64 is 4 to the power of 3, to the power of 3. So I will write this one in this form because we are trying to use this relationship. So we have to write this one. If we can, we have to write this one in exponent form. Another thing is I can write this one as to the power of 6. We can write it this way. But the thing is, since this is base 4, I wanted to when I write this one in exponential form, I wanted the base to be the same with this one. And that's why I chose, instead of this one, I chose this 4 cube. And this is 4 to the power of x. Okay, this one. And then what is this one? When we bring this one, well, this is 1 over, right? This is on the denominator side, but I can bring this one on the numerator side. And to do that, what we do is we change the sign of this exponent from +3 to -3. So this negative means actually this is 1/4 cube. It's not 4 cube. Okay, so we have 4 to the power of x. Now let's go back to this one. We have b to the power of x equals to b to the power of y, implies this. And we have our base 4, and we have these two exponents. So since the base are the same, this implies x has to be -3, so that these two numbers will be equal. Okay, that means we have solved, because our x is this number, right? Our x is the whole thing that we wanted to evaluate. So we solve this. So this means This is basically -3 when we evaluate this one. Okay. So this relationship is so important, this equivalence property. We use it to simplify or solve logarithmic or exponential expressions and equations, of course. Okay, so we have two commonly used logarithmic forms or logarithmic functions. One is the so-called common logarithmic function, and the other one is the natural logarithmic function. The common is when the base is 10, and the natural logarithmic form is when the base is e. Okay, e is the natural number, the number that we learned in our last lecture, which is 2.7818, something like that. Okay. So if the base is e, we call it natural logarithmic function, and we write it as ln. Okay, instead of writing log base e, something like this, we write it as ln x. Okay, this is what we, so whenever you see ln, that means there is a base e. And the common logarithmic function is log 10, log x, the base 10, and this is basically log x. We don't write the base here. Okay, so for these two, we don't write the base. They are known, they are commonly used ones. Okay, so when you see this one, that means the base is e. When you see this one, that means the base is 10. Now, knowing this, let's simplify these expressions. The first one, we have log 100 million. Well, we have this log 100 million, and we wanted to simplify or to evaluate this one or simplify this one. So here, since there is no base here, that means this is base 10. Therefore, I will change this one to well, I will use the same variable y. So I will change this one to exponential. So let's take this 10 to here. So we'll have 10 million equals to 10 to the power of y. Now we need to write this one in exponential form. That means 10 to the power of how many zeros do we have? There are 8 zeros. So this is 10 to the power of 8, 10 to the power of y. Therefore, this implies y is 8. And that's what we have right here. And similarly, when you have ln 1 over e cubed, this is equals to -3. Well, first, let's we don't have this. This is the answer. So we assume we don't have this one. So ln 1 over e to the third is x. Then now again, the base here is e. So what I'm going to do is e to the power of x. This means now we need to rewrite this one. So that will be -3 equals to e to the power of x. So e is -3. So as you can see, this equivalence relationship is so important and it's so useful. And we use it to solve or to simplify not only exponential expressions, but even logarithmic function expressions. Okay, and here are some important properties of logarithms. The first one is log 1 to the base b, any b, doesn't matter what that b is always 0. Always log 1, the base b is 0. And the reason is when you convert this one, if we try to evaluate this, we will have, if we write this one in exponential form, 1 equals to b to the power of x. Or, well, let's say we have this number b. It doesn't matter what that b is. It's between 0 and 1 or greater than 1. So for what value of x will this number always be 1? Well, that one is when this is true only when x is 0. Therefore, here x is 0 because I can write b 1 as b to the power of 0. We can write 1 as b to the power of 0. Therefore, x is 0. So this is always true. For any b, well, b has to be, of course, or b has to be greater than 1. And the other one is log b to the base b. The same, if we have the same here, same argument and the same, the base and argument are the same, then this is always 1. For example, if we have log 3 to the base 3, this is always 1. And log b to the x base b, these two are the same, then this is, we can, this is always 1. Okay, this is always, sorry, this is always x. Whatever x this x is, because we know this is 1, log b base b is 1, and we can bring this one down here. We have this property. Okay, we have this property, another property. It's not here, I guess. So log, let's say, b a to the x is the same with x log a to the base b. Okay, so if you have exponent here, you can bring this exponent down here. Okay, we will learn this one in I think it's I put it at the end. Okay, and another property is b to the power of, if we have b to the power of all of it on as exponent x b. Now if this b and this b are the same, this is kind of, we have exponential form b to the power of the whole thing, and then we have the logarithmic form as an exponent. Then this is always x, which is this number. Okay. All right. Now the next is looking at the graphs of logarithmic functions. So let's start with the one that we know already, which is the exponential functions or graphs of exponential functions, because we said these logarithmic functions are inverses of exponential functions. So if we have an exponential function which is given in this form, b to the power of x, where b is greater than 0 and b is different from 1, then we can, using the same technique that we learned how to find an inverse function, we can find the inverse function of this one by replacing this f of x by y, and then switching this to x and y, which will give us x equals to b to the power of y, and then we solve for y, and that will give us this one, because now we know this is exponential form, so I can change this one to logarithmic form, and that one will be log x to the base b equals to y. These are the same, right? Because we know now, we learned the relationship between exponential and logarithmic. So that this is what we call an inverse function of this one, or this one is an inverse of this one. Both of them are inverse of each other. Now, if we have y equals to log x to the base b, this is an inverse of y equals to 2 to the power of x. Okay, these two functions are inverse of each other. So for y equals to the power of x, which is an exponential function, this is the graph. We know it always passes through the point y equals to 1. And for the logarithmic form, log x to the base b, again, it passes through 1, and it goes this way. And as you can see, this is what we have, the symmetry along this y equals to x line. Okay, so these are the logarithmic functions. For exponential functions, the x-axis was the horizontal asymptote, but now for the logarithmic functions, the y-axis is the vertical asymptote. Okay, as you can see, this is the vertical asymptote. And if the base is between 0 and 1, like this, for example, 1/2, here it's an increasing function. As we go from left to right, it's increasing, and here it becomes a decreasing function. Okay, and still this is symmetric along this one. As you can see, this part is an image of this part, and this part is an image of this part. Okay, so again, it's symmetric along this y equals to x line. And of course, we can do the shifting as well. Once you know the graph of the base function, then we can use the transformation. And we always know if we add or subtract, if we subtract a number inside the function, well, f of x minus 1, for example, if we have something like this, then this one shifts the graph to the right, always by 1 unit. So in this case, this subtracting -1 from this inside part shifts this blue graph to the right by 1 unit. So the blue is y equals to log x base 3. So this is the base function. We start without this -1 and -3, okay? And that's what we call the base function. And then we start, the next will be shifting to the right by 1. And that will be, we shift it to, from 1, it goes to 2. And the vertical asymptote, originally it was the vertical y asymptote of y-axis, but now it becomes the line y equals to, x equals to 1. This is the line x equals to 1. So instead of the y-axis, now the asymptote is, vertical asymptote is x equals to 1 for the red line, right? And then the next is we go to this, and this one we know it shifts the graph because it's negative. It shifts the graph 3 units down. Therefore, we will shift this red graph down by 3 units, and that's what we have right here. So we just shift the red because the blue is the original, so we are on the red line now. So from the red one, we shift down 1, 2, 3. 1, 2, 3. 1, 2, 3. So every point will shift down by 3 units, and then finally we have this green line, and still the asymptote doesn't change. The asymptote is the line y x equals to 1. Okay. And well, how about the domain of a logarithmic function? We know for exponential function, the domain is, if we have f of x equals to b to the power of x, then domain is between -infinity to infinity. Well, all real numbers. And the range is between 0 and positive infinity. Now, the next is, how about f of x equals to log x base p? We said these two functions are inverse of each other. And for inverse functions, these two things, they switch. So the domain for this one will be the range for this one. The range for this one will be the domain for this one. So domain for this logarithmic function becomes 0 to infinity, which is this one. And the range becomes that one, which is -infinity to infinity. Okay. Therefore, this is what we have. The domain for this logarithmic function is greater than 0, basically, which means if we write this one in interval notation, this is what we have, 0 to positive infinity. And the range is all real numbers, and you can see the range from here. If you look at this one, it's going down infinity, down forever. And if you look at this, it's increasing, which means it's going up forever. Okay, therefore the range is all real numbers. Now, one thing that we wanted to know here when you determine the domain of a logarithmic function is, originally when we defined a logarithmic function, we said x and b, both of them, they have to be positive numbers, positive real numbers, right? These two numbers. Therefore, when you write log x base p, these two numbers, they have to be positive. But now we are mainly focused because we've talked a lot about b, about the base b, and we said it has to be greater than 0 and it has to be different from 1. And this x, the argument x has to be greater than 0. Okay, always x has to be greater than 0. So when you have something like this, log 8 minus x, we may have some expression like this, or more complicated than this one. So what we need to do, or what we need to know is, whatever we have inside this logarithm, it has to be greater than 0. So in this case, this 8 minus x has to be greater than 0. And then the next is to find the domain of this function. We just need to solve this one, this inequality. And we know how to solve an inequality, right? So because this is just simple linear inequality, we will solve this one. So moving this one to the other side, we will have negative x greater than negative 8, and then multiplying both sides by -1 or dividing both sides by -1. It will cause us flip this inequality, which will be less than. Therefore, this will be positive x, this will be positive 8, which means x is less than 8. And writing this one in interval notation is between -8 to positive 8. Okay. And if we have something like this, which is a bit complicated or more complex than this one, so what I need to do is, what I need to make sure is that this guy right here has to be greater than 0. So we start with that one. 4 minus x squared should be greater than 0. And well, what is this? This is 4 minus x times 4 minus x, right? Greater than 0. And well, we know how to solve this one, right? We know how to solve this one. Well, there are different ways, of course, because this is easy. It's a square root, so we can easily determine what values of x makes this one positive. But to make it more general, what we do is we solve for each of this. For this one, it will be 0 at the point x equals to 4. And again, this one is 0 at the point x equals to 4. At the point x equals to 4, yes. Therefore, what we do is, let's say we have 4 here. Just I'm trying to make this one more general, right? Otherwise, the simplest way is, because this is square, so the only thing that makes this one positive is 4 minus x. Either this one is greater than 0 or 4 minus x is less than 0. Okay, so instead of determining this way, suppose we write this function or this expression as a product of linear factors like this one. Then what we do is we find the roots of this one, or the zeros of this one, and those are, for this, in this case we have only one, so that's 4. And what we do is x minus 4 for numbers, sorry, this is 4 minus x. For numbers below 4, this is negative, right? For numbers below 0, below 4, this expression, this 4 minus x is 0 because it's negative. For example, what you could do is you try it. You take one point, for example, since 0 is below 4, and that's the easiest number that you can pick here, 4 minus 0, sorry, this has to be positive, sorry. So 4 minus 0 is positive. So all numbers below 4, if we substitute them in here, they will be positive. And at the point x equals to 4, it will be 0. And on the right side, it will be negative. Okay. And the same, the other 4 minus x is 4, 4, 0, negative, negative. Now, if I multiply these two, what we get is positive times positive, it will give us positive. 0 times 0 is 0, and then negative times negative is positive. And the question is, for what value or in which range is this one true, greater than 0? So we don't want to include this one because it's only greater than 0, not greater or equal to. So it's positive only in this range and in this range. This range is negative infinity to positive 4 with parenthesis, not close the bracket. And this is 4 to positive infinity with parenthesis again. And in between, we put this union sign, okay? And that's what we have right here, okay? All right. And other important properties of logarithms are, one is the product property. This is very important, and we have to be able to write expressions like this one in this form. And this says, if we have product inside the logarithm, inside the parentheses, then we can write this one, or we can split them up, and we can write this one as log x, the base b, the same base, plus log y base b. So here it was multiplication, x times y. Now it becomes here positive addition. So be careful. If we have log x plus y base b, log x base b plus log y base b. This is not true. Okay. If you have this, if this is plus, then we cannot write it this form, in this form. We cannot distribute it. Okay. So this is, be careful, this is wrong. But if you have x times y base b, this is the same with log x base b plus log y base b, and we call this the product property of logarithms. Okay. And a simple example to that we can use this for is, let's say we have log 5 times 25 base 5, and log 5, because we have answer here already, times 25 base 5. Okay. So this we already know, of course. We know this one, we can multiply it, and we can use the exponential form. We can convert it to exponential form. But I will use this product property, and I will write this one as log 5 base 5 plus log 25 base 5. So log 5 base 5, this is b and b, and we learned this one because log b base b is always 1. So the first one is 1, and the second one is log 5 squared base 5. Again, we learned this one. 25, I can write it this form, 5 squared. And here we have the same base here. Base and argument are the same, and we have the exponent. Therefore, this is whatever we have here. And this is what one of the properties that we learned earlier. Therefore, this is basically the same, equals to 3. Okay. And going the other way, again, another example, log 100 AB. Again, we can write this one as log 100 plus log A plus log B. So here, when we distribute them, you may ask, what base do we choose? Because we don't have base here. Normally, of course, here we have a base. So what we do is, this is the same base, base 10, even though we don't write it. So here we have base 10, and here we use the same base. We don't change the base. Okay. Therefore, we have log 100 plus log A plus log B. Log 100 base 10 is 2, and those are, since they are constants, we just leave it that way, and we have this simplified form of this one. And the other property of logarithms is the quotient property, and that one is for y different from 0. Well, we don't want y to be 0, so that it will be undefined. But if we have this expression, then this is the same with this one. Now, in this case, the addition in the product rule or product property becomes subtraction. Okay. Other than that, they are more or less, they are similar. It's the same, similar idea. So we can again apply this one in different or in simplifying expressions. For example, if we have log 81 over 3, of course we can simplify this because 81 over 3 is 27. So we can simplify it, but we wanted to check if this works. So using this rule, this is basically log 81 base 3 using this rule property minus log 3 base 3. So 81 is 3 to the power of 4. 81 is 3 to the power of 4. So instead of 81, I will write log 3 to the power of 4 base 3. And this is, well, since they have the same base, this is just 4. Therefore, this is 4. This is 1. 4 minus 1 is 3. And on the other hand, 81 over 3, we can simplify this, and we have 27. So we have log 27 base 3. And 27, we know it is 3 cubed, right? 27, 3 times 3 is 9. 9 times 3 is 27. Therefore, log 27 base 3 is log 3 base 3 cubed. Again, these are the same. So this is just 3, whatever we have right up here. Therefore, from the right side, we have 3. From the left side, we have 3, which means the answer is true. So this is true, that means, right? And that this is what we call the quotient property. And using the natural logarithm, ln e to the power of e over 5, we have, again, I can apply that property because this is division. So we have ln e minus ln 5. Now, what is ln e? Well, ln e means log, you don't need to write it this way, but just to see what we are doing, this means log e to the base e. That ln means the base is e. And in this case, you can see these two are the same. The argument and the base are the same. And when the base and the argument are the same, then this is 1. So ln e is always 1. Okay. Therefore, here I have 1, and ln 5, I will just leave it that way because this is not a rational number. You can use your calculator to find this number, but you don't need to do because you will write the rounded number, the approximate number, right? It's not the exact number. So it's okay to leave it this way. And another important property, the power property of logarithms. And this is what I was talking earlier. So if we have log x to the base p, log x to the power of p base b, this is the same with, we bring this one down here, p times log x to the base b. Okay, we can write it this way. So this is always very important. All these properties, they are very important when we solve or simplify the logarithmic expressions or equations. Okay, we can have even logarithmic equations. And well, let's see. Let's say we have log 4 squared base 4. Now this one, 4 squared is 16, and log 4 to the power of 16 is 2. And on the other hand, we can bring this one 2 using the power property, we can bring the tool down here in front of the log. So this is what we have, 2, then log 4 base 4. And this one is, since we have the same argument and base, this is just 1. So we have 2 times 1, which is 2. Okay? Therefore, these two are the same. So this is another important property of logarithms. Now let's see with this one. Let's check this one. We have log the 7th root of x cubed base 6. Okay. So what is this? First, let's rewrite this one. This is log base 6 x to the power of, now the square, the 7th root, we can write it as 3/7 because that means 1/7, right? And now using the power property, I can bring this one down here, and we can write this one as 3/7 log x the base 6. So this is basically this one, which is much more simpler than this one, just to see, because this is just a coefficient. In this case, it was a root, 7th root, but now it's just a coefficient. And here we have log x base 6. And similar for this one, we can just rewrite it this form. And yeah, and for this one, we can write it this form. Okay. All right. This is, let's say if we have log x squared, this is 2 times log x. And the graph for this one is, we have 2 of them. One is this, going to the left, another is this, going to the right. Okay, because this is the domain. The domain for this one is between -infinity to 0 to positive union 0 to positive infinity, except the value 0, because the value 0 makes this one 0, undefined. Okay, therefore it's not in the domain. Okay. And well, this is summary of all this, most of these properties. We have this property that we learned earlier. We have the product property. We have the quotient property, the power property, and the rest that we learned earlier. Okay, so all together that means. So let's say we have this expression right here, and we wanted to write this one as a sum or difference of logarithms. So let's do it here, because I already did it down there, but let's do this one. So here we have quotient of two numbers, the top and the bottom. So I will use the quotient property, and I will write this one as ln cube root of xy minus ln wz square. Okay, and we can further write this one as, because this is sum or difference of logarithms, so I can further write this one as using the power property. First, let me write it this way: ln xy to the power of 1/3 minus ln. Now we can distribute this one because this is w times z square. So we have product of w and z square. So by using the product property, I can write this one as ln w plus ln z squared. The reason why is this bracket is because we have negative, so this negative we need to distribute it And for this one, using the power property, I will bring the 1/3 at the front, and we have ln x y minus, now distribute this one, ln w minus ln z square. Now again, I will use the power property here, 1/3 ln x plus ln y minus ln w minus, again, let's use the power property here. So we'll bring the 2 here, and we have ln z. And now I will distribute this one, 1/3 ln x plus 1/3 ln y minus ln w minus 2 ln z. Okay, so as you can see, we wrote to the we arrived to the simplest form of the logarithmic forms, and we wrote this expression as sum or difference of logarithms. Okay, and now we should be able to go back as well. Okay, if we are given this form, for example, we should be able to get back to this one, and that is just by using this property again. For example, I can bring this 1/3 here just using the power property. Okay, and I can do the same thing with this one, and then I can convert this, or I can change this addition to multiplication by using this property. So we should be able to go back to the original expression, and this is what we have for that example. And yeah, these are the properties that we use it in each and every step. Okay, all right, so yeah, so we have one more example here, and this is to write this expression as let's do it together, to write this expression as a single logarithm and simplify it. So we have log 150 minus log 3 minus log 5. So let's start with this one. Well, we have difference of 2 logarithms, and this is what we call well, first let's factor out this one. It doesn't have to be that way, but we can do that one. But anyway, either way, you will get the same result. So I will follow just from going from right to left. Now, using the quotient property, if you have difference of 2 logarithms, that means it's log, we can put them together, and that will be log 150 over 3 minus log 5. And we can simplify this one, and that's 50, right, minus log 5. And again, we have differences. So I will use again the quotient property, and this, using the quotient property, is just 50 over 5. And again, simplify this inside parentheses, that is log 10. And what is log 10 now? What base do we have right here that we don't write? That's 10. And the base and the argument are the same. Therefore, this is 1. And that's what we have right here. Okay. And here what I used is that we factor out negative here. I kind of approach it in a different way. We factor out negative here from this 2. So we have negative log 3 plus log 5. And using the product property here, we add them, we multiply them up. So we have log 15, 3 times 5. And then using the quotient property, we have 150 over 15, and that will give you 10. So we have log 10 is 1. And that's how we go back. If we are given as a sum or product of logarithms, we can combine them using or by applying all the properties. Okay. All right. So this is all for this lecture, and Yeah, see you in the next lecture.